Hello everyone. In today's lesson we're going to be taking a look at the question, do action-reaction forces cancel? And we're going to use this question as a context to explore systems in physics. So, the question we have here is, do action-reaction forces cancel? After all, they're equal in magnitude and opposite in direction, and we've seen in previous discussions that when vectors have the same length, same magnitude, but opposite directions or are anti-parallel, that they cancel out. So is that the case with action-reaction forces? The first thing we need to understand before we can answer this question is that in order for forces to cancel, they have to act on the same system. So let's write this out. Forces can only cancel if they act on the same system. So what is a system then, would be the question that follows. System is just whatever we want to study, what we want to focus on. So it could be an object, it could be a group of multiple objects, collection of multiple objects. It's up to us. We get to decide what we want to study, what we want to observe. So consider this simple example. We have a person pulling a wagon. We could define the system of interest for this example in multiple ways. We could say that the system is the wagon. We want to look just at the wagon. So in this case, we would draw a free body diagram. What are the forces acting on the wagon? So let's do that. Let's get a dot for our wagon. Actually, let's draw it over here underneath the wagon. So we'll draw a dot to represent our wagon, and we're going to draw some force vectors on this dot to represent the forces that act on the wagon. So first of all, there's going to be the gravitational force acting on our wagon. So weight equals mg downward. There's going to be a normal force directed upward, equal and opposite to the weight because there's no acceleration in the vertical direction. There's going to be a pulling force from the person on the wagon. So the person's pulling on the wagon in this example, pulling to the right. So we'll call that P for the pull force from the person. And then there's going to be frictional resistance between the wagon and the ground, opposite the direction of motion. We'll go with a little f for friction. So we've got our four forces acting on our object. The dot there is our wagon. And we can use the force diagram then to determine what the net force on the wagon is. So in this case, the normal force and the weight, mg, for the wagon cancel out. The net force would be the pulling force from the person minus the frictional resistance between the wagon and the ground. Okay? So when we define our system this way as the wagon, we're looking only at the forces that act on the wagon. So the question then is, are any of those forces part of an action-reaction pair? And what I want to focus on right now is the pulling force. The person pulls on the wagon. So let's do this in a different color. Let's use green. And I'm going to draw the force on our diagram this time. So we've got a force from the person on the wagon. So you might wonder, is the frictional force then the reaction force for that action force? And the answer would be no. And we can very simply figure this out by thinking about force pairs. Action-reaction force pairs are always part of a mutual action between two objects. So in the case of the person pulls on the wagon, the two objects that are part of the interaction are the person and the wagon. So the reaction force would have to be the wagon pulls on the person. The person pulls the wagon forward, the wagon's going to pull the person backward. So let's draw the reaction vector in here. Oops. Person pulls forward on the wagon, wagon pulls backward on the person. So that is an action-reaction pair. Go back to our original statement here. Forces can only cancel if they act on the same system. If we look at this action-reaction pair, only one of those two forces acts on the system of the wagon. Person pulls the wagon forward. That force acts on the system of the wagon. But the reaction force, the wagon pulls the person backward, well, that would be acting on a different system, the system of the person. So these action-reaction forces would not cancel out as a result. The frictional force is not part of that action-reaction pair. Instead, it's part of another action-reaction pair between the wagon and the ground. So we have to be really careful when we're looking at systems and looking at force diagrams, whether or not forces are in fact action-reaction pairs. And we have to realize that in most cases, action-reaction pairs will not cancel because they don't act on the same system. And that's this key concept over here. Forces can only cancel if they act on the same system. So most of the time, forces that are part of an action-reaction pair won't cancel because those action-reaction forces will act on different systems. However, there are exceptions. So let's consider a different system. Get rid of all my work here. Oh, I can only go so far back. Oh, that's okay. We'll have to do a little bit of erasing here. So now, instead of just looking at the system of the wagon, I want to look at the combined wagon-person system. So I'm going to make my system a little bit bigger here. And now I'm looking at this combined system of the person pulling the wagon and the wagon. If I look at that same force pair from before, so we had person pulls on wagon, wagon pulls on person, equal and opposite forces, part of a mutual action. In this case, if I'm considering the combined system of the wagon and the person, neither of those action-reaction forces acts on that system. Instead, these forces are internal to that system. They are inside the system that we are interested in. So this is another key concept, another key point when we're looking at Newton's third law and systems in physics. If you have an action-reaction pair that is inside a system, those forces will cancel. In fact, this is the only time that action-reaction forces will ever cancel, if the action-reaction pair is internal to the system that we are studying. So, if we're looking at the combined system of the wagon plus the person, this action-reaction pair is internal to that system, and it will cancel out. It can't accelerate the system. Remember from earlier, only forces that act on the system or are external to the system can accelerate it. So let's add that over here in terms of the system, external to the system. Only forces external to a system can accelerate the system. So a real simple example of this, let's say your car breaks down. Your car won't start. And you need to push your car across the parking lot so that you can get to your friend's vehicle and jump it. Let's just say that your friend can't move their vehicle over to you. You've got to push your vehicle, right? We're going to make it a little harder than it needs to be. If you sit in the driver's seat and you try and push on the dashboard, you're not going to move your car because that action-reaction force pair, you push on the dash, the dash pushes back on you is internal to the system of your car. But if you get out of your car and push on the back bumper, you can now accelerate the vehicle, if you have enough force, overcome friction. This is because now your push is outside of the system of the car, and only forces external to a system can accelerate the system. So if we look at the combined system of the wagon plus the person, and we consider the external forces acting on the system, well, sure, there's going to be weight and gravity, right? And it would be the combined weight of the wagon and the person in this example. So this is the combined weight, mg, of the person plus the wagon, normal force equal and opposite. What would be the other forces, though, that are acting on this combined system? Well, first of all, the person is going to walk. And when that person walks, their feet push backward on the earth. Now, the reaction force from that would be that the earth pushes forward on the person's feet. And that force comes from outside the system that we're studying. So that would go on our diagram. This is the force from the earth on our feet, pushing our feet forward. There's also going to be frictional interaction between the wheels of the wagon and the ground, and that frictional interaction is going to resist the motion of the object, so it's going to be the opposite direction that the wagon will tend to move. And that's an external force. The frictional force is coming from outside the system. So we have a slightly different force diagram now when we consider the combined system of the person plus the wagon. Only forces external to the system can accelerate it. So these internal forces that we talked about before, person pulls on wagon, wagon pulls on person, they cannot accelerate the combined wagon-person system. So I know this is all a little bit tricky. So let's try and break things down a little bit here. We can look at three different systems for this example. We can look at the system of just the wagon, like we did earlier. We can look at the system of just the person, or we can look at the combined system of the person and the wagon. So right now we're looking at the combined system of the person and the wagon. Let's go ahead and list all of the forces that act within and outside of this person-wagon system. So we already have one action-reaction pair up there. That's the person pulls on the wagon pulls on the person. Between the wagon and the ground, there's going to be frictional resistance. So we saw that earlier. There's going to be a little bit of frictional force acting backward on the wagon here. And there's going to be a reaction to that action force. So there's going to be a similar frictional force on the earth, but pointing in the opposite direction. Now, we know the earth doesn't move, so it doesn't really have the same effect, but it's there nonetheless. There's a third action-reaction pair that we're interested in here as well. The person, as they walk, will push back on the earth. So we're going to label that capital F. And the reaction force here would be that the earth pushes forward on the person. Now we would have weight vectors and normal vectors, so the gravitational force and the normal force on both the wagon and the person here as well. But we're going to ignore those forces because they're going to cancel out, and it is going to cause our diagram to become very cluttered very quickly. So we're going to leave those out for now. What we want to look at is, if we consider each of the three systems, the system of just the wagon, the system of just the person, and the combined system of the wagon and the person, what is the net force on each system? And remember that only those forces that are external to a system can accelerate it. So, we already have the combined system wagon plus person here circled in yellow. So let's use yellow to write out the net force on that combined system. Remember, we can only look at forces that act on the system of the wagon plus the person. So the two green forces here, person pulls on wagon, wagon pulls on person, those will not apply to our wagon plus person system because they come from inside the system. Remember that internal action-reaction forces cannot accelerate a system. So the green forces are out. That leaves us with the purple forces and the blue forces. So let's look at the blue forces here. We had the person pushes on the ground. Does that force act on the system of the wagon plus the person? And the answer is no. It acts on the ground. But the reaction force, the ground pushes forward on the person, does act on our system of interest. And it's external to the system, so it can cause an acceleration. So one force that we have here is the force from the ground on the person. So let's look at the third set of action-reaction forces over here in purple. This is the frictional interaction between the cart and the ground. So we had the frictional interaction resisting the motion of the cart, so to the left in our example, and resisting the potential motion of the earth to the right. Now we know the earth doesn't move, but if it were to move, as a result, it would move to the left, and friction therefore would act to the right. So, which of these forces, if any, is going to go into our net force equation for the combined wagon and person system? Well, force has to act on that system. And the frictional force that acts on the ground, again, acts on the ground. It's not acting on our system. But the frictional force that acts on the wagon is acting on our system and is external to that system. So it will factor into our net force calculation. Now you'll notice that these two forces, the frictional force and the force from the ground on the person, are opposite in direction. So I'm going to subtract the frictional force down here to get my net force equation for the combined system. So the net force on the system of the wagon plus the person would be the force from the ground on the person minus the frictional force on the wagon. So let's take a look at how this would work out for a different system. Let's now look at the system of just the person. We'll do this in orange. So we're looking at just the person. Now remember, only forces that act on this system can accelerate the system. So we can eliminate a bunch of forces already. The forces that act on the ground, so frictional force here, the force from the person on the ground here, are eliminated. They don't act on the person. They can't accelerate the person. The forces that act on the wagon, the frictional force on the wagon, the pulling force from the person on the wagon, they don't act on the person, and they can't accelerate the person as a result. So that leaves us with just two forces. The force from the ground on the person, capital F, and the force from the wagon on the person. Remember, the wagon pulls backward on the person. We didn't label those earlier. Let's label those forces with a P for pull. So because the pulling force from the wagon on the person is opposite the direction the person moves, we're going to subtract it to get a net force equation of big F minus big P for the person. So the force from the earth on the person, acting forward, and the force from the wagon on the person, pulling backward. The difference between those two forces will be the net force on the person. We have just one system left. This is the one that we considered earlier. Remember, we had already written an equation for this one. That was the system of the wagon. And we had come up with an equation, a net force equation for the wagon, of the pulling force from the person minus the frictional force. And that's going to be the same equation we come up with here. The forces that act on the earth cannot accelerate the wagon. The forces that act on the person cannot accelerate the wagon. Only the forces that act on the wagon can accelerate the wagon. And those are the pulling force from the person forward and the frictional force resisting the motion of the wagon. So we have three different equations for the net force on three different systems in this example. So the net force equation all depends on what system we're studying, how we want to define our system. And we could set each of these equal to mass times acceleration, according to Newton's second law of motion. And here's the really cool thing about this. Because these objects are connected, the acceleration is going to come out the same in each of these three calculations. How is that possible? Well, remember that the wagon and the person will have different masses. And as a result, the combined wagon plus person system will have a different mass as well. So three different masses for three different net forces, but the same force to mass ratio will get the same acceleration. Okay, so that's our lesson on Newton's third law and systems. If you have any questions, you can email me or talk to me before or after school.